In this section, we construct the Smith chart. Consider the transmission line shown here. The positive z direction is taken to the right. The line extends from z equals 0 to z equals L, and the load impedance z sub L is connected at the end. The characteristic impedance of the line is z sub 0. At an arbitrary position z, we can define the impedance looking toward the load, and also the reflection coefficient at that point. The reflection coefficient gamma of z is defined as z of z minus z sub 0 divided by z of z plus z sub 0. If we divide the numerator and the denominator by z sub 0, we can write this expression using the normalized impedance. The normalized impedance z tilde of z is z of z divided by z sub 0. Then gamma of z is z tilde minus 1 divided by z tilde plus 1. For a lossless line, the reflection coefficient can also be expressed as the ratio of the reflected wave to the incident wave. It is v2 over v1 times exponential of j2 beta z. Conversely, z tilde is 1 plus gamma divided by 1 minus gamma. The normalized impedance can also be written using the wave traveling in the positive z direction and the reflected wave traveling in the negative z direction. Now, when we work with a transmission line, we often want to know the normalized impedance if the reflection coefficient is known, or to know the reflection coefficient if the normalized impedance is known. We may also want to know the impedance or the reflection coefficient at an arbitrary point on the line. If we had a diagram that shows gamma values on the normalized impedance plane or normalized impedance values on the gamma plane, we could read the relationship without calculating it every time. This is the motivation for the Smith chart. Let us decide which plane is more convenient. The normalized impedance is R tilde plus Jx tilde. The real part R tilde is the normalized resistance. Because negative resistance is not possible, R tilde ranges from 0 to infinity. The imaginary part X tilde is the normalized reactance, and it ranges from negative infinity to positive infinity. Thus, the normalized impedance plane is the right half plane. On the other hand, the reflection coefficient gamma is the ratio of the reflected wave to the incident wave. Its magnitude cannot exceed 1. Magnitude 0 means no reflection, and magnitude 1 means total reflection. Therefore, gamma always lies inside the unit circle on the complex plane. This makes the gamma plane much easier to use. Also, if the reflection coefficient at a point z sub 1 is known, and another point z sub 2 is displaced by delta z, then gamma at z sub 2 is gamma at z sub 1 times exponential of j2 beta delta z. Therefore, moving along a lossless line rotates gamma by 2 beta delta z without changing its magnitude. For this reason, it is convenient to draw normalized impedance values on the gamma plane. This drawing is the Smith chart. Next, let us construct the chart. The relationship between normalized impedance and reflection coefficient is given by the following equations. This is a bilinear transformation. A bilinear transformation maps generalized circles to generalized circles. Here, the only singular point is gamma equals 1. Except at that point, the mapping is conformal. Therefore, if two curves intersect at right angles on the normalized impedance plane, their images also intersect at right angles on the gamma plane. To draw the Smith chart, we draw the constant resistance lines and the constant reactance lines on the normalized impedance plane and find their images on the gamma plane. A simple way to do this is to choose 3 points on each line, map those 3 points, and draw the circle through the 3 image points. First, consider constant resistance lines. For R tilde equals 0, we use 3 points. When Z tilde is 0, gamma is minus 1. When Z tilde is J, gamma is J. When the magnitude of Z tilde goes to infinity, gamma approaches 1. The circle through these 3 points is the unit circle. Thus, the imaginary axis of the Z tilde plane maps to the unit circle in the gamma plane. Next, consider R tilde equals 1. When Z tilde is 1, gamma is 0. When Z tilde is 1 plus J, gamma is 1/5 plus J 2/5. Again, the point at infinity maps to gamma equals 1. The circle through these 3 points is the constant resistance circle for R tilde equals 1. Next, consider R tilde equals 3. When Z tilde is 3, gamma is 1/2. When Z tilde is 3 plus J2, gamma is 3/5 plus J 1/5. Together with gamma equals 1, these points determine the constant resistance circle for R tilde equals 3. Now consider constant reactance lines. For X tilde equals 1, we use points that have already appeared. The point R tilde equals 0, X tilde equals 1, maps to gamma equals J. The point R tilde equals 1, X tilde equals 1, maps to 1/5 plus J 2/5. The point at infinity maps to gamma equals 1. These 3 points determine the constant reactance circle for X tilde equals 1. For X tilde equals 2, Z tilde equals J, 2 maps to 3/5 plus J 4/5. Z tilde equals 3 plus J, 2 maps to 3/5 plus J 1/5. Again, the point at infinity maps to gamma equals 1. These points determine the constant reactance circle for X tilde equals 2. The negative reactance circles are mirror images with respect to the real axis. Using these circles, we can read impedance values directly. The point gamma equals 1 corresponds to infinite impedance, so it is the open circuit point. The point gamma equals -1 corresponds to 0 impedance, so it is the short circuit point. The point gamma equals 0 corresponds to Z tilde equals 1, so it is the match point. If a reflection coefficient is given as a point on the Smith chart, we can read the normalized resistance and normalized reactance from the constant R tilde and constant X tilde circles. Conversely, if a normalized impedance is known, we can plot its corresponding reflection coefficient on the gamma plane. A Smith chart is obtained by drawing many of these circles inside the unit circle.